Assalamualaikum and good morning to all.
Morning, Doctor.
Alright,
Boleh Yusuf.
Salam doktor.
yeah. So I would like to announce again, today is our last day to have class together. Starting from next week, Dr. Siti Manis will take over this class. She will cover the topic of non-linear system and jitter control system. Okay, so hopefully by today we are finished starting from the first week by introduction of the state space, and then today we will complete how to design a controller to the state space equation. Okay, so you can see the progress lah. Before this, on the first week of the lecture, when I talk about state space and so on, you never know. You don't have any idea about the state space. However, starting from a few weeks ago, you already understand what is the state space, kan? Betul tak? You have the idea of the state space, and then you have some experience. Although it's not a good experience, when you are simulating the system to the MATLAB, okay. However, I believe you have some idea how it looks, okay. Although you didn't have the whole idea, what about the answers, what is the output graph, so on, is okay. All right. However, although this is the last class for us to, we have our last class, I will upload another video, okay? Today, I will explain to you the first controller. The controller is pole placement controller. However, in the other video, I will explain to you about the observable controller. Okay, yeah, so in this course, you will learn about two controllers. Firstly is a pole placement. The second is a observable controller. Observable controller. All right, so I will share my screen. All right. So in this chapter, you will learn about firstly, pointer option, there's the option. Firstly, you will learn about the conditions before you need to implement the pole placement controller to the system. You must know the conditions, and then after that, you will learn about the steps to implement the controller to the system. There are two of them, the conditions before you can apply pole placement controller to the system. And next, after you learn about the first topic, then you go to the second topic, you will learn about what is the steps to implement the controller to the system. Okay, so we go by one lah. Okay, so far you have learned about two types of the system, electrical system and mechanical system. And after that, you convert this system to differential equation. And then you obtain the state space of the equation. Okay. Actually, there is another one here, from state space to transfer function. And then from the transfer function to the state space. And then after that, you do the analysis such as the stability of the system only, right? And then on last week, you convert the state space. You convert the state space to a few different state space forms. However, I just highlight to you how to convert the state space to phase variable form and also the observable controller, observable canonical form. There are only two. The rest you just need to know lah. Okay. And then after that, today I will focus on to implement the pole placement controller to the system, and then the other video, I will upload the video about how to implement the observable controller to the system. Okay, so far can you follow our progress for this course?
Yes, Doctor.
Okay, Doctor.
Yes, Doctor.
All right. So actually, what is the pole placement controller? Okay, I need to change my. Okay, actually, this is a block diagram obtained from state space equation. Okay, so can you see here? This is starting from here. You multiply with B, you got B U. Then starting from this line, multiply with A, you got what this? What is the equation you got? Anyone can respond? From here, from this point, go backward or feed forward to this gain A, and what you got at this point?
XA.
It's XA, or the normal we call that A X, is it? Okay. So after this junction, this is combination between this input and the second input, is it? So what is the outcome of this part? You have the first input here, and then you have the second input here, and then the sign is positive and positive. So what is the outcome of this summation part? Anyone?
X plus BU.
AX plus BU, is it? AX plus BU. Okay. Actually, this is equation equal to x dot equal to x dot. So you can see this is coming from here. X dot equal to AX plus with BU. Okay. And then the output here, Y, actually Y equal to what? When you see this flow chart or the block diagram, Y equal to Y here equal to what? Anyone?
CX.
Y equal to Cx. So actually, this is referred to this part, because normally we assume we always get D equal to 0, is it? So that's why Y equal to Cx only. So it means that this is the block diagram of the state space. If you have a state space, x dot equal to Ax plus with BU, Y equal to Cx, where D equal to 0, okay, this is your block diagram. Actually, this is your block diagram. Okay, so this is the block diagram for a system. Okay, so what's happened when we apply pole placement controller to a system? We have a system, then we apply the pole placement. So this is the block diagram of a system with pole placement controller. Okay. I would like to ask Mana partisipan ni? I would like to ask Ahmad Aiman bin Ahmad Asri. Okay, what is the difference between figure A and figure B? Can you tell me what is the difference between figure A and figure B? Ahmad Aiman. Or anyone would like to try what is the difference between figure A and figure B? You can see from the figure. Yes, the difference is the negative K feedback. So it means that if you want to implement pole placement controller, you just add negative K feedback only to the system. So it means that the pole placement controller is really easy. By implementing the negative K feedback to the system here, by implementing negative K feedback to the system, because this is the original system. However, when you want to apply or implement pole placement, you just need to add another negative K feedback to the system, then you get the pole placement controller. Senang kan? So, in this case, how to design, what we need to do in order to design the pole placement controller. Okay, this is the reference lah, because the original system did not have any feedback K. However, the pole placement controller have a feedback K here. So, to design this controller, we just need to obtain the K values only. So what you need to do, you just need to obtain the K values only. After you get the K values only, then you already design the pole placement controller. So this is our objective. Okay, this is our target in order to design the pole placement controller. Okay, so at the end, regarding to the question and so on, you just need to find the K values only. Alright. So this is example lah. This is example of the signal flow graph. Okay. If you can see that at the figure A, the signal flow graph for a system, original system lah. Okay. Actually, this is referred to the feedback here. Refer to the A matrix. Okay, and the forward here, feed forward here, refer to the C matrix. And then this is refer to the B matrix. If we compare to the previous, we have B, we have A, we have C. We have B, we have A, we have C. Okay, so how about K? How about K? So the difference between the figure A and figure B, you can see that there is a feedback K here. K1, negative K2, and negative K3. So it means that how many of the K values that you need to determine depends on the order of the system. Order of the system. So in this case, you have third order system. You have, because how you know this is third order system? Because you can see this is the first integrator, second integrator, and the third integrator. So that's why we know this is the third order system. Okay, so this, because this is third order system, then you need to determine 3K feedback values. Okay, let's say if your system is fault or the system, fault or the system, so you need to determine negative K1, negative K2, negative K3, and negative K4. Okay, so K is a set of the feedback gate values. That's the meaning of the K. Alright, so example, convert the system to a signal flow graph. Then apply the pole placement controller to the signal flow graph. Okay, firstly, I want to ask Mio Muhammad Firdaus. Mio, what is the order of the system? Mio, can you tell me the order of the system? What is the order of the system? By looking at the transfer function. Ada jawapan dekat chat box ke? I need to look at. Dalam tadi Google Meet. What is the order? Third order system, yep. So this is third order system because you can see that the highest at the bottom is S power of 3, kan? S power of 3. So what you need to do, firstly, you need to change lah. From this one, you just multiply at the bottom the numerator part and numerator part together, and then this is your transfer function. After that, you convert the system to the phase variable form. Okay, this is the phase variable form. After you convert this transfer function, hopefully you can refer to the previous lecture how to convert. Okay, and then after that you can draw lah the signal flow graph. So you can see that when you want to draw the signal flow graph, you must starting from U input and end with the output Y. Okay, so you need to do the same. You must starting with the input U. Saya tulis Ctrl Z. Boleh padam tak? You must starting with U and end with the output Y. Okay, starting with U and end with the output. Because this is third order system, you need to draw 3 integrators. 1, 2, 3. You need to draw 3 integrators. Integrator number 1, integrator number 2, and then integrator number 3. So you just connect them together. Okay, so because you need to starting from left side, from the right side, this is x1. This should be, what is the value here at this part? If this x1, here will be, anyone? This part should be, we must starting from x1, okay, from the right side. If x1 before the integrator will be what?
X dot
X what?
X dot 1.
X1 dot X dot 1 sama boleh. Okay. Normally to the table, we say that X1 dot equal to what at here? X1 dot. If you still remember the table, you have X,
X2.
X2 and X2. Okay, X2. Okay. And here will be, Boleh you can answer the question straight away. No problem.
X2 dot
X2 dot here will be
X3
X3, and finally you get at this part X3
dot
dot. Okay. And then after that, regarding to this one, to this state space you obtain, yeah, you know that this is referred to x1 dot, this is referred to x2 dot, this is referred to x3 dot n. So you know that x1 dot here actually equal to x2, then because you know that x1 dot equal to x2, okay, settle. The second line here, x2 dot equal to x3, then x2 dot equal to x3. However, the x3 dot here actually refer to negative 4 x2 minus 5 x3 plus with u t, kan, untuk x3 dot. So you know that this is your location of the x3 dot. Okay, this is your location. So the x3 dot actually come from negative 4 x2. So this is location for the x2, negative 4. And then negative 5 x3. This is location of the x3. So you just feed back negative 5. Okay. And then plus with u. The gain is 1. So this is u, the gain is 1. Okay. And then after that, done for the x dot part, then we go to the output. Output is 100 x1 plus 20 x2 only. So this is your location of the x1. So the gain must be 100 x1. And then the second part is 20 x2. So this is the location of the x2. So you just forward, go to the y. So the gain is 20. So now this is your signal flow graph for the system. Okay, so you already answered the first signal flow graph question. Then you need to apply the pole placement controller to the signal flow graph. Okay, so I just want to ask you, how many feedback gain that we need to apply to this system? Koh Teng Cheng, how many feedback gain that we need to apply to the system? Koh Teng Cheng?
dua.
Huh? How many? Lavanya, how many Lavanya feedback gain K we need to apply to the system?
3.
Why Lavanya?
Sebab third order system
Yeah.
got 3 integrators.
Yes, that's correct. Because this is third order system, you need to apply 3 feedback gain. Thank you Lavanya. Okay, so you need to apply the feedback gain at U, input here. So where you need to start? You need to start from x1. Okay, from x1 you have the first negative K1. Okay. And then you need to apply the second feedback gain from X2 to the input. This is the second feedback gain. And finally, you need to apply the third feedback gain starting from X3. And this is the third feedback gain. This is negative K3. So this is the system with pole placement controller. So this is the answer. So you understand that in order to draw the signal flow graph, you need to draw the original system. Okay, original system, and then after that you need to apply the pole placement. So in this case, you already know the rest of the values except negative K1, negative K2, and negative K3 values. Other than that, you already know 20, 100, the gain of 5, the gain of 4, and so on. You already know from the transfer function. However, you don't know what is the value of negative K1, negative K2, and negative K3 only. So this is what you will try to do until the end of the class. Okay, so I need to take 5. Okay, so see you another 5 minutes. Emergency. Alright, so we continue again with the lecture. Okay. Okay. So, what is a pole placement? What is the use of the pole placement controller? Let's say you have an unstable system, so you want to stabilize the unstable system lah. So you just need to apply the pole placement controller by in certain condition. Okay, but there is some condition when you want to apply the pole placement controller. However, if you want to stabilize the linear system, you just can apply the pole placement because it will manipulating the post location of a system. So it means that this is original system. Let's say this is the pole location, something like that. Okay. However, when you apply the pole placement will modify this original system post location become maybe something like this. Maybe something like this lah. So you can see that this is system with pole placement. This is system without pole placement. So this is how pole placement are used to stabilize the unstable system. You can see the pole placement. So it means that this is the old controller, then it placement the pole to a new placement. So you can understand the controller name, the controller function based on the controller name. So that's what you call pole placement. Okay. Next, the pole placement also used to improve the transient response. Okay, so what is the meaning of the transient response? So let's say this is the original system. Okay, this is the transient response. The transient response is caused about the percentage overshoot, the setting time, and so on. So you can see that this is quite high for the percentage overshoot, or maybe the setting time quite long. Okay, so how you want to, when you apply the pole placement, you can modify the percentage overshoot, the setting time of the system to whatever you want. So this is the use of pole placement. So let's say the percentage overshoot here of the original system without controller about 20% overshoot. However, you don't want 20% overshoot, you want 10% overshoot. So you can use the pole placement. Let's say the setting time about 10 seconds. You want to make it faster, you want to reduce to 5%, 5 seconds. So you can do it by using the pole placement. So what you need to do, you just apply the pole placement, and then you can see that this is 5 seconds, and the percentage overshoot here become from 20 become 10%. So this is the use of the pole placement controller. Okay. But however, I would like to remind you that you have to use an additional controller if you want to eliminate the output error. So let's say, what is the meaning of this reminder? Where is my pen? Okay. What is the meaning of this reminder? So let's say you have this kind of error. Although you improve the transient response, however, you have this error. Okay, this error. You cannot use pole placement controller only in order to eliminate the error, because pole placement used only to improve the transient response and also to stabilize the unstable system only. Okay, for some of the function. So you need to add another controller to this system or to this pole placement in order to eliminate the error. Okay, one the thing you already learned in control one is a PID controller, because PID controller can use to eliminate the error. Okay, so I want to tell you that this part, when you want to implement the controller, this is your lab number 2 about. This is lab number 2 about. So in your lab 2, you need to simulate a system without the controller, and you need to design the pole placement controller to the system, and then you need to simulate. Okay, this is your lab number 2. However, when you look at the yellow box here, this is your project. So you need to design the pole placement controller. However, the pole placement controller did not help to solve the error problem. Okay, so you need to apply another controller such as PID, whatever you want, in order to eliminate the error. So this is your group mini project. Okay, so in conclusion, you have 2 reports that you must submit. So the first one is lab number 2, and then after that you need to submit the mini project report. Okay. Okay. So now we want to implement the pole placement controller. Okay. So this is now we want to focus on this thing lah. So before you want to implement the pole placement controller, you must make sure these conditions are fulfilled. Must fulfill. Not one of them, not none of them. You must make sure these 2 conditions apply. Okay, firstly, you must make sure the system must be in phase variable form, state space. And then the second condition, you must make sure the system is a controllable system. So it means that if the system is uncontrollable, or you can say that not controllable, so it means that you cannot apply the pole placement. You can take the system and throw to the trash bin. Okay, so you only can apply the pole placement to any controllable system only. Okay. So what is a controllable system? So we look at here. Pole placement controller only can be applied if and only if these conditions are fulfilled. Okay, example number 2. So we check whether the system can use the pole placement controller. Let's see how we want to check it. So this is the same transfer function from the previous example. So we need to convert the system to the phase variable form. After that, step number 2, check the system controllability to fulfill this condition. So this is the formula for the controllable. Okay, I put C because C refer to the controllable. So you need to find the determinant of the C matrix. The C matrix is combination of B, AB, A square B. This is the thing you must remember lah. If this determinant not equal to 0, then the system is controllable. Okay, example lah. From this step 1 or the question, the B matrix is B. You already get the B matrix. Now you need to calculate the AB matrix. So you just take A matrix, multiply with the B matrix, then you get this answer. Okay, you already get the AB matrix. And then after that, you need to calculate A square B matrix. A square B matrix, okay? The third one, A square B matrix. Actually, A square B matrix is a A matrix multiplied with the AB matrix. So you take A matrix and then you already have the AB matrix answer here. AB matrix here, is it? So A matrix multiplied with the AB matrix. So you got this answer. This is A square B matrix. Okay. It's easy how to check the control system controllability. So, at the end, I can conclude that to check the system controllability, if you have the second order system, you just need to get B and AB matrix only. Okay. If you have a third order system, you need to calculate B, AB, and A square B. If you have fourth order system, you need to calculate B, AB, A square B, and A cube B. So I believe you understand lah the pattern. B, A, B. B, A, B, A square B. B, A, B, A square B, A cube B, and so on lah. If you have fifth order system, so you need to calculate from B up to A power of 4B. Something like that. Okay, now we already have B matrix, AB matrix, and A square B matrix. What's happened? We need to do. Okay, so you just need to replace lah. This is B matrix, this is AB, and this is A square B. And then after that, we calculate the determinant, we get -1. The answer is -1. So it means that this is not equal to 0. So we can conclude that this system is a controllable system. Hence, the pole placement controller can be used to the system. Okay. So how to calculate this one? Use the 2T technique to determine determinant. Firstly, we extract this matrix. Okay, this matrix here. After that, we select a row or column, whatever you like. However, I want to use this one because it's easy, because have many zero there. And then after that, I just write down 0, take the row information here. Okay. And then after that, I apply the sign, positive, negative, positive. Finally, I get the answer is -1. So this is how I calculate the determinant of the C matrix. We use
Doktor,
system.
kalau pilih yang lain dapat tetap -1 ke?
Ya, saya rasa. Dia akan dapat -1 juga. Kita cuba ya, we try. Let's say we want to use this 0, 1 and -5. Saya put 0, 1, -5. Bila 0 ni, we don't care lah. We don't care. For 1, you will get 0, 1, 1 and 21. And after that, if we choose at the -5, we get 0, 0, 1 and -5. -1. So the answer same. Although you choose any row or column, the answer will be same. Okay, untuk tu, for that.
Ya, Doktor.
Okay. Next. Now we already know that the transfer function can already fulfill the requirements. The transfer function already convert the transfer function to the phase variable phase, and then the second condition, the system is controllable. Next, the final part, we can design the pole placement controller. Okay, so I can see that the internet connection problem just now. Okay, according to this, okay, for the first part here, we have the meaning of it is a composited system or original system or system from the question. So regarding to this one, the source to solve the first part is the question lah, GS. So in this case, the GS is 20s plus 100 s cube 54. So this is the source for the first part. So you need to refer to this thing in order to solve the first part. 20s plus 100 divided by s cube plus 5s square plus 4s. Okay. When you have this information, then you can go to the step number 1, then you can go to step number 2, step number 3, and the final step. Okay. So for the source, in order to solve the question, the second part, you need to extract the design criteria or requirement such as percentage overshoot, setting time, peak time, and extra from the question. Then calculate the damping ratio and natural frequency based on the requirements lah. So, as I told you before, according to the previous slide, this one kan. So, according to this slide, firstly, the original system, it means that the first part lah, tell you that you have 20% of the oscillation, percentage overshoot. However, you want this system become 10% overshoot. So this is the meaning of the desired. What you want or your desired lah. And then after that, you want the setting time from 10 seconds to 5 seconds. So this is what you want or your desired design. So if we focus on this one, according to whatever I tell you before, so it means that this is the original transfer function, and then example, let's say the percentage overshoot is 20%. When you run this, you simulate this wind thing. However, you want to have about 10% overshoot and 5% the setting time. So that's why you need to extract the design criteria. So it means that the design criteria is 10% overshoot and 5% setting time. And then based on this, because you have TS and percentage overshoot, if you still remember the formula of the percentage overshoot and the setting time, you can calculate these two values, damping ratio and natural frequency. Yeah. Next, after you have this damping ratio and natural frequency, so if you still remember in control 1, you learn about this equation. This is the characteristic equation for the second order system only. Second order system only. So every time when we talk about the characteristic equation of the second order, we always refer to this this equation. S square plus 2 zeta omega ns plus omega n square. Because you already the x zeta, you already have the damping ratio, natural frequency, you just replace to this equation and then you can get the characteristic equation of the composited system. Okay. After that, when you get the characteristic of this one, then compare the characteristic equation with the characteristic equation of the composited system. Then you need to find the K values. So this is the step lah. Okay. All right. So we look at the first part again. You have the uncompensated system. In this case, this is the uncompensated system. And then you need to convert to the phase variable phase and check the controllability. Okay. And then after you change to the phase variable form, then you need to inject the gain K to the system and then you get this equation. So this equation, the system with the pole placement, this system without pole placement, This is with, this is without pole placement. After that, you need to determine the characteristic equation of the system with the pole placement. After that, you get the characteristic equation, and then you need to compare these two equation in order to obtain the K values. Okay, this is just the step lah. However, I will show you how to calculate everything. All right. So far, I think we need to have 5-minute breaks before we go to the example. How to solve the before we go to the example, I need to explain this thing. Okay, from the original system transfer function, I mean from the first part here, how you want to inject the gain K to the transfer function or to the original system, you just need to replace U equal to minus Kx. Minus K ni always refer to the pole placement controller. So let's say this is your original state space in phase variable form. So what you need to do, you need to replace U with negative Kx. U with negative Kx. Where K equal to K1, K2, K3 depends on your order of the system. Let's say third order system, you need to have 3 Ks. If you have second order system, you need to have 2 Ks and so on. Okay. After you apply the pole placement, just replace U equal to negative Kx. Finally, you get this one. negative kx lah, because you replace ut equal to negative kx. And then after that, you just factorize the x, and this is the system with pole placement controller. And this is a new A. So because we know that x dot equal to ax, we compare this one lah, x naught, x dot, x, x. And this is your new A. Okay. So your new A for the system with flow placement is A minus BK lah. So step number 2, obtain the original system characteristic equation. This one lah, determinant SI minus A if you refer to the original. However, from the step number 1, the new A is A minus BK. So finally, this is your new characteristic equation for the original system. So that's why it becomes determinant SI minus A minus BK. So that's why you get this thing, this step number 2 here. This thing, A minus K. That's why you got the state space of the system with pole placement here, because of this lah derivation. Alright. Okay, so I think we need to wait about, we have a break about 5 minutes. I will stop recording this class, and I will continue to record for the example. Okay. Alright, see you in another 5 minutes.